Hello and welcome to the third part of a series of videos aimed at developing a Bomberman-style game in vanilla JavaScript, using the canvas element. In the last video, we mostly focused on adding bombs to the game. This meant allowing the Bomberman to drop bombs and use them to destroy everything around him, including nearby blocks, creating chain reactions with other bombs, and unfortunately even himself. With the main game mechanics now in place, we can turn our focus to the main aim of the tutorial series, making a great multiplayer experience the series is infamous for. So in today's video, we'll add a number of power-ups that will be revealed upon destroying the blocks scattered throughout the stage. These can be picked up to enable players to gain advantages over other players. Speaking of which, we'll also add those other players to the game too, so that we have some competition. And finally, we'll wrap it up by adding the game state, so that we can keep track of the players' scores, and allow us to show them within the HUD at the top of the screen. So let's jump in. My name is Anthony, and why don't you join me in my corner of the web, where I like to build stuff in the browser with the latest technologies. If you're a regular viewer of my channel, you'll know that I always recommend to build and then refactor your code as you go, once you have a better understanding of what you have so far, and its solution to the problem you're attempting to solve. So to accommodate the new additions we're looking to add today, let's first refactor some of our code to make this a little easier on ourselves. As we potentially want to add multiple stages to our game, let's go ahead and create a stage object shape or model that allows us to support this. In the level data constant file, we'll first go in to completely remove the collision map array. This might feel a little strange, but as you know, this is a one-to-one mapping of the tile map array above, so it's probably better that we auto-generate the collision map based on that data, rather than maintaining it manually in a separate array. Before we do that, however, we'll also wrap the tile map within an object called stage data. This object will allow us to group all the stage details in one place moving forward. Again, building a common shape that we can use for other potential stages. For example, we'll next add a property called max blocks and give it a value of 50. You might remember we already have a max blocks constant value, and yes, this property will look to replace that constant, so go ahead and remove that also. To allow us to auto-generate the collision map, we'll be exclusively using the map to collision tile lookup object above, so it's necessary that we add all the collision tiles for each of the tiles we use in the tile map array, which to be fair, we're only missing the outer wall tile, so we'll add that and map it to the wall collision tile. Opening up the stage class next, we'll make the required changes to the code to work with the new stage data object. We'll first remove the unnecessary imports from the level data constant file and replace them with the stage data object. For the local tile map and collision map class properties, we can no longer use the imported arrays, so we'll use the structure clone function on the stage data's tiles property so that it creates a deep copy of that array. Then for the collision map, we'll map over the same tiles property, row by row and tile by tile, and use the map to collision tile lookup object to create the converted array using the collision tile values, basically replicating the array we've just removed from the level data constant file. Moving down the code a little now, let's move our attention to the stage's block generation code. We're currently doing this with the add blocks and add block to tile at functions. These are called from the build stage function, which in turn is called from the constructor. However, this responsibility should be ideally with the block system class, as this maintains the blocks within the stage. So continuing the refactoring session, we'll next move these functions to the block system class to follow the single responsibility principle. With that knowledge, we can safely remove the build stage function and replace its call within the constructor with the build stage map function instead. We'll then in the block system class add a new constructor parameter called getStageCollisionTileAt and assign it to a local class property with the same name. This function reference comes from the stage class so that we can query its collision map array. It will be used by the block functions we'll now move over to this class. I'll paste them here under the constructor and remove them from the stage class. We'll then import the required references from the level data constant file and include the new stage data object. For consistency, we'll rename the addBlocks function to addBlocksToStage and call it within the constructor. Okay, let's now continue to clean up and fix the moved code and any of its references. We'll first remove the blocks variable within the addBlocksToStage function and update any of its references to use the class's reference instead. We'll also replace the maxBlocks constant value with the stage data's maxBlocks property too. Finally, for this function, we'll swap the tilemap property, which no longer exists, with the stage data's tiles property. Then in the addBlocksTileAt function, we can go ahead and replace the collision map references with the new getStageCollisionTileAt function reference, as we know this will eventually query the same array. We'll also need to update the updateMapAt reference to use the local stage reference too. In fact, let's move this call to the function below and rename the add_block_tile_at function to isBlockAllowedAt to keep it pure. We can then simply use the continue statement instead, skipping the rest of the code in this loop cycle. So far so good. Although, with the code we've just added, we're now using the blocks array for different things at the moment. One to hold the initial stage block cell positions, and again for the actual block entities, for when they are destroyed. So for the last refactor, let's look to change what we hold within this array. Instead of pushing either of these, we'll now push an object instead, which holds both values. In the add_blocks_to_stage function, let's update the push function to include a cell property and an entity property. In this instance, we're adding the block to the stage, so the cell will hold its initial position, and its entity will be undefined, as we know the block is currently in its alive state. With that change in place, let's look to update the rest of the class. In the add function, we'll update the push function here too. As we're destroying the block at this point, we'll set the entity's property to the new block instance. However, before we can do that, we'll obviously need to find the corresponding block's array index first. To do this, we'll use the array's findIndex function and match the row and column values from the cell being passed into the function with the instances in the block's array. If the index is less than 0, we know no block has been found, and therefore we can exit the function. For both the main update and draw functions, we'll add the entity property to the block's update and draw calls. Although, as this property might be undefined, we'll add an optional chaining operator after the entity's property, to ensure no error is thrown. Then finally, in the remove function, we'll first rename the block parameter to destroyedBlock to properly describe the value being passed in. We're unable to use the indexOff function here due to the changes we've made, although we can use the same index logic we added below to the add function. So let's copy this across in its place and correct the variable references. And just before we continue, let's not forget to pass on the new function reference we added to the constructor parameter list. So in the battle scene class, we'll add the stage's getCollisionTileAt function reference to the end of the block system argument list. And with that, we should be ready to test our changes. So let's open up the browser for the first time today and see if we've broken anything. And phew, the game still seems to be working as expected. We don't have any errors, and Bomberman can still move around the map and blow up the stage's blocks. However, this time, we've now amended the code in preparation for the first change we'll do today, adding power-ups to the game. If you're familiar with the game, you probably already know that power-ups randomly spawn from soft blocks when they are destroyed, and their locations are randomly chosen at the start of the round. In the original game, this was limited to just 2 power-ups in the battle mode: the bomb, which increases the number of bombs the player can drop at any one time, and the flame, which increases the bomb's flame length. However, this list was extended to include a whole host of other effects in later games. When a power-up is spawned though, it will flash with 2 frames of animation, and be positioned in the same cell location as the original block it was hidden behind. It will continue to sit there until it is either picked up by the player or unfortunately blown up by one of their bombs. Either way, it will be removed from the stage. However, if the player does pick it up, its effects will be applied to them, hopefully giving them the advantage over the other players. For our version of the game, we'll go one step further however, and include a third power-up, the skate or speed power-up, which increases the velocity the player can move. With this information, we have a guide on what we'll need to implement within our version of the game. Back in the level data constant file, we're going to add 3 new properties to the collision tile enum object. As you can see, these all have a prefix of power-up, and represent each of the power-ups we'll be adding into the game today. You may be asking, why are we adding these to the collision tiles? Well, we'll actually be replacing the cell value in the collision map array with these values when a power-up spawns from a destroyed block. This means, just like the wall collisions, we'll be using the collision map to detect if the player and power-up occupy the same cell location. We can then revert the collision map cell value back to the empty value if they are, and apply the necessary effect. This tile-based collision for the power-ups replicates how the original game did it, so I thought, why not do the same in our version? One thing to notice is that the power-up properties all have a lower value than the wall property, meaning the player will be able to walk through them and therefore allow the power-up to be collected. Next, we'll move down to our new stage data object, and add a new property called power-ups. This will contain a list of power-ups we'd like to add to the stage. This continues the trend of making our stage completely configurable. For this tutorial however, I've added each of the power-ups and a value I think works best. But by all means, go ahead and change these as you see fit. To contain the power-up logic, we'll create a new system class called PowerUpSystem, and just like we've done previously, we'll use the SDC-EC snippet from the template, rename the class and remove any unwanted code. We'll also add the usual remove and add function stubs in preparation for later, along with an empty power-ups array to store our instances. At this point, it's probably wise to actually get the sprites we'll be using for the power-ups in the game. And as you can expect for this, we'll jump over to the Sprites Resource website and navigate to the same Bomberman page as before. The power-up graphics are located at the bottom of this page. Simply click on the icon and download a copy of the image on the next page to your project's image folder. Once done, back in the Project Explorer window, you'll notice I've renamed it powerups.png. Naturally, we'll also need to add a reference to it in the HTML file too, via an image tag, so that the browser will load it at runtime. I've also given it an ID of power-up, strangely enough. Then, back in the power-up system class, we'll continue as we've done before and add a reference to it using the query selector function. Okay, with the code prepared, let's head back to the block system class and randomly add the power-ups to the stage's blocks. We're going to create a new function called add random power-ups to blocks, and call this in the constructor, naturally after the blocks have been added, as we'll need them to be created first. Inside this function, we'll now loop over the stage data's power-ups property we've just added, using the object's entries function. This will give us an array of the collision tile value, or rather the power-up type, and the amount of these we wish to add to the stage. We'll then use another for loop inside this for the index of the power-up we're adding. Before we can add the power-up, we'll obviously first need to pick a random block that will contain it. We'll add a small helper function to do this for us, called getRandomBlockIndex, which, as you can guess, will return an index for one of the blocks within the blocks array. This function will use the mathRandom function to simply pick a value between 0 and the length of the blocks array. Once we have this block index, let's next set up the new property for this object called powerup. This property will hold the collision type value, or powerup type, this block will contain. This means if the property is undefined, we know the block does not contain a powerup. So just for completeness, let's also add this property to the push function within the add blocks to stage function. With the powerups now allocated to randomly selected blocks, we'll next look to make them spawn once their containing block has been destroyed. In the remove function, we're going to add a call to the new function called handleSpawnPowerup, where we'll pass on the index of the destroyed block. Inside this function, we'll first see if the block has a powerup by checking if the block's powerup property is undefined or not. If it isn't, we can simply exit early. Although, if it is, we'll make a call to a function called addPowerup. We'll pass on the block's cell location and powerup type. So where does this addPowerup function come from? Well, this is the add function in the powerup system class, which we'll again pass on to the block system class via its constructor. Knowing this, we can now complete the add and remove functions there. Inside the add function, we'll simply push a new object entry to the powerups array, using the powerup type and the cell location we've passed on. Inside the remove function, we'll do the same as we've done before, and use the indexOff function to find the powerup index, and remove it from the powerups array if it was found by using the splice function. To connect this all together, in the battle scene class, we'll next add a new instance of the powerup system class in the constructor. As we need the add function reference from the block system class, we'll add it above that class's instantiation, and then pass on the add function reference as the last argument. Finally, back in the block system class constructor, we'll mirror this change by adding the new parameter called addPowerup and assigning it to a local class property, which in turn is exactly what we'll be calling within the handleSpawnPowerup function. Nice. Okay, let's next look to draw the powerups to the screen. Normally we'd create a new entity for this, much in the same way as we've done with the block system and its block entity. However, for powerups we won't be doing this. Instead, we'll be drawing them directly within the class, using the powerup's type value as the identifier. The main reason for this is that no matter what powerup we choose, they are fundamentally all the same. The only difference is the sprite we need to draw to the screen, and the effect that gets applied once they are picked up. This makes them much easier to manage, and allows us to share the same animation between them, and to be fair, this basically replicates how the original game did it. Let's quickly look at the image we downloaded earlier again, and primarily at the top 3 powerups. You'll notice our collision tile values match the sequence of the sprites, flame being first, then bomb, and then the skate. To be fair, this was done on purpose, again to make it easier on ourselves, as we won't need to manually manage any frame map objects, as we would normally do for our entities. For now though, we'll just focus on the flame tile at the top left hand corner. One thing to notice is that we have a padding of 8 pixels around the edge of the image, something we'll need to acknowledge as we'll be manually drawing these sections of graphics to the screen. Knowing this, back in the draw function, we'll loop over the powerups array and use the templates draw function to draw the flame section of the image to the screen. For the time being, we'll simply draw the same flame sprite for all the powerups, just to test if our powerup code is working as expected. As per normal, we'll pass on the context and image data, and for the section dimensions, we'll use the value of 8 for both the X and Y positions to accommodate the padding we mentioned earlier. And for the size, we'll use the tile size constant value, as we know the power-ups are the same size as the tiles. Finally, for the position values, we'll use the cell, column and row values and multiply them again by the tile size constant value. And for the last step, within the main draw function in the battle scene class, we'll now call the power-up system's draw function, passing on the context and camera arguments. And with that, let's see what we've accomplished so far. As the Bomberman walks around the stage, destroying the various blocks scattered around it, you'll notice some of these will now spawn our randomly placed power-ups. Great stuff! Whereas we know these are all currently showing the flame sprite, we do unfortunately have a bug at the moment. We're not checking to see if a power-up has already been allocated to a block, which means that there's potential for us to reuse the same block and therefore overwrite what we've had previously. As you can see here, we've ended up with 17 power-ups rather than the expected 20 that we defined. Okay, let's jump back to the code and fix this. In the add random power-ups to blocks function within the block system class, we'll add a while loop and continue to increase the block index until we find a block that does not contain a power-up. Notice that I'm using a modulus operator to ensure we don't go out of the array's bounds. And there you go, that should fix our placement issue. Now that we know the power-ups are working, let's also add the flashing animation and draw the correct sprites for the power-ups before we jump back to the browser. Starting with the animation, at the top of the power-up system class, we'll add the usual animation frame property and set it to 0. We'll also add a frame delay constant value with a value of 8, which we know is the number of frames each frame of the flashing animation will be shown on screen. Then in the main update function, we'll do as we've done previously, and call a new function called update animation. This will constantly flip the animation frame value between 0 and 1, when the time's previous value has exceeded the animation timer property value. Finally, we'll also set up the property's initial value within the constructor, and pass on the time property to the power-up system class from the battle scene class. Moving on to the power-up sprite next then, in the main draw function, we'll alter the draw frame's dimensions array to adjust the x and y offset values based on the animation frame and power-up type variables. Just for clarity, let's bring up the power-up's image file again. We're using the power-up type value for the y position, as we know this matches the sequence of the frames from top to bottom. As for the x position, we'll use the animation frame value, as we know this flips back and forth between 0 and 1. Hopefully you can see how we've set this up makes maintaining this class much easier to manage. Finally, we'll now add a call to the update function from the power-up system class to the battle scene class's update function, so that the game can run its animation code. Checking the results in the browser now with these changes, I've already destroyed all the blocks by the way, you can see we now have our 20 power-ups scattered across the stage, and they are correctly showing their corresponding image and flashing as intended. Great stuff. We just need to allow the Bomberman to pick them up now, so let's do that next. Opening up the Bomberman class, as we now have the power-ups available in the game, we'll first reset the Bomberman property back to the default value of 1. Then we'll create a new function called getCollisionRect. This will provide any consumers with a dimensions object of the Bomberman for collision purposes. This will include an x and y position, along with a width and height dimension. We're using the half tile size constant value here to get an 8x8 collision box in the middle of the player. Next, in the battle scene class, we'll add a players array, which will eventually hold all the different coloured Bomberman entities currently available in the game, but for now, this will just hold our white Bomberman. More on this soon. We'll then pass this on to the power-up system class, as we know we need to have access to the player references for collision purposes. We'll then change the current player property, which is now redundant, to use the new players array instead. We'll then push an instance of the Bomberman entity to it. Finally, within the update function, we'll wrap the player function call with a for of loop and remove the this prefix. We'll also do exactly the same within the draw function. Let's now jump back to the power-up system class and add the collision code for the power-ups. First though, let's add the new players parameter to the constructor and add a local reference to it. Then in the update function, we'll call a new function called hasPlayerCollided, which will hold the collision code. Inside this, we'll use a set of for of loops, one for the players array and one for the power-ups array. Following the same change we just made in the Bomberman class, we'll add the same function, getCollisionRect, to this class too. Again, this will provide us with a collision object with the dimensions of the necessary power-ups instance. Here we'll use the column and row cell values for its position, along with the tile size constant value for its dimensions. We can now simply use a rectangle overlap function supplied with a template, along with the necessary getCollisionRect function calls, to check if the player has collided with any of the power-ups on the stage. If they have, we'll call the remove function, which we know will remove it from the power-up array, and therefore from the game. If you need any more information on the rectangle overlap function, I have a dedicated video you can watch if necessary. If I have remembered to do so, there should be a link attached in the video description. Let's open the browser and see if this works. As the Bomberman walks around the stage, revealing power-ups from destroyed blocks, we can now walk over them and they'll correctly be removed from the game. Nice. So the last thing we need to do is apply their effects to the player, so let's add those now. In the same hasPlayerCollider function, we'll add a call to a new apply power-up function on the player entity class, passing on the current power-up type. We'll create this in the Bomberman class, where we'll apply the necessary changes based on this type. We'll use a switch statement and a cage statement for each of the collision tiles we currently support. For the flame type, we'll increase the bomb strength by 1. For the bomb type, we'll increase both the bomb amount and available bombs properties by 1. And finally, for the speed type, we'll increase the speed multiplier property by 0.4. Open up the browser to see the results. As Bomberman reveals the power-ups once more, if we walk over them, their effects are now applied to the player based on their type. We're able to place more bombs, and their flames increase as expected. We can also gradually walk faster by picking up the skate power-up. Great stuff. With the power-ups now working, let's now add the other players so that we can finally put our bombs to good use. We'll start in the controls config file that comes with the template, and add the necessary controls for the other players. By default, this file is configured for 2 players, so we'll just need to add the remaining 3 control objects to cover all 5 players. To save on time, I'll copy across what I've set up previously, although you can go ahead and change or amend these values as you see fit. It should be noted that all the gamepad objects will be set up and configured the same, as the browser recognises each connected gamepad individually, although for the keyboard, the OS of the browser can only use the default, meaning we're limited to just one keyboard. So yeah, trying to find 5 sets of the controls on one keyboard was somewhat difficult. Then, within the Bomberman constant file, we're going to make some small adjustments to cater for all 5 of the differently coloured Bombermen. We'll start by adding a new enum object called Bomberman Colour, and list each of the available colours, from player 1's white colour through to player 5's green colour. Next we'll add a lookup object called Bomberman Player Data, which will at the moment list all the starting column and row positions for each of the available Bomberman colours. Then we'll move our attention to the set of animation frames, which currently only covers the white Bomberman. We'll need to extend this to include the frame data for all the other different Bombermen. I'll again copy and paste the data to save myself from retyping it out, so please go ahead and pause the video if you wish to copy it. Notice that we're no longer using the map object here though. We are instead using an object called Bomberman Frames. It splits each set of the frames by the Bomberman's colour enum value. The reason for that is that this object will eventually be used as a reference object instead. To show its use, let's add an exporting function at the bottom of this file, called getBombermanFrames. This will take a Bomberman colour enum value as its parameter, and return our missing frames map object. We'll then simply spread the Bomberman Frames object values from above, based on the colour supplied. So if we want to get the necessary animation frames, we can now simply request it with this function instead. In the Bomberman class, let's go ahead and update the setup code in the constructor to work with these new changes. To start with, we'll no longer need to pass on the position value, as we now have this information predefined in the Bomberman Player Data object. So we'll swap this parameter out with an ID parameter instead. As we'll have multiple Bombermen on the stage, this ID value will be used to identify each player, from 0 to 4. Then within the supercall, we'll update the X and Y values to use this object's row and column values instead, based on this ID value. Next we'll add a few new local properties to accommodate our changes too. First will be an ID property to store the assigned ID. Then a colour property, which again will use the Bomberman Player Data object to get the necessary colour defined for this ID. And finally we'll add a frames property and call the getBombermanFrames function to get the necessary animation frame data based on our assigned colour. Now that we have a local frames property, let's ensure we're using it within the draw function. So at the bottom of the class, we'll add the this prefix to the frames variable. And just before we move on, let's also clean up the imports from the Bomberman constant file. Okay, within the battle scene class, let's again update the initial code to accommodate the Bomberman changes. We'll first add a new function called addPlayer and move our current Bomberman instantiation code over to it. We'll again swap the position arguments with the ID arguments we've included on the function parameter list. Next, in the game constant file, we'll add a new constant value, noPlayers, and set this to a value of 5. This, as you can expect, controls the number of players we'd like to have available within the game. Then finally, back in the battle scene class, we'll use a for loop to iterate over this value to add the required number of players to the game. And with that, let's open the browser once more to see what we've accomplished. Right from the start, we can now see all 5 players at their starting cell positions, each with their own unique colour. Nice! We can also either use the configured keyboard or gamepad controls to move them round simultaneously, blowing up blocks and picking up any of the dropped power-ups, although this is a little difficult with one pair of hands. At this point, I think you can agree, we are pretty close to replicating most of what we set out to accomplish. That said, I think we're missing one last thing, the HUD at the top of the screen, so we can see the player's scores, and more importantly, who's winning. So let's jump back into the code and add this last feature for today's video. Starting in the game constant file, we'll add a new constant value called max wins, and give this a value of 3. As you can expect, we'll use this value to determine the number of wins needed to complete a game. Then in the main Bomberman game class file, we'll add a new game state object that will keep track of the game's current state, which at the moment will be the player's win information. For this reason, it will hold two properties: wins, which will hold an array of each of the player's win total, where we're just filling with zeros at the moment, and max wins, which we'll just set to the max wins constant value for now. We'll next move the scene property into the constructor, and pass on the new game state object to the battle scene class 2. In that class, we'll mirror the changes, and add a state argument to its constructor, and assign it to a local state property to hold a reference to the overall game state. We'll then pass this onto the HUD class 2, along with the time object, as we'll also need that for the countdown timer. Inside that class, we'll again mirror the changes we've just made, by adding the necessary arguments in the constructor, and again assign them to local class properties. We'll replace the position variable as it's not needed, as the HUD is fixed to the top of the screen, so we'll use zeros for both the X and Y values. We'll look to add the countdown timer first, so let's now also add a clock number array and give it values of 3 and 0. This will be used to hold the minutes and seconds for the countdown timer, so this equates to 3 minutes and 0 seconds. And to complete our class setup, we'll now create a clock timer property and use the time object to give it a 1000 millisecond delay, which in time terms equals 1 second. Let's now add a call to a new function called updateClock, which will be used to update the clock array and simulate the time ticking down to 0. As per usual, this will use the time object to check if the delayed timer has elapsed, which we know will be 1 second, and exit early if not. If it has, however, we'll deduct 1 from the second's value in the clock array and reset the delayed timer with another 1000 milliseconds. Then we'll check to see if the seconds value is less than 0, and if so, deduct the minutes value by 1 and reset the seconds value to 59, because that's how generally clocks work. Moving on to the draw function, we don't currently have a way to draw text to the screen, which is something we'll need to display the clock timer. So for this, in the utils folder, we'll create a new file called drawText which will do just that. We're doing this in a separate file as this could be eventually extended and reused to draw any text for our game moving forward. Inside this file, I'm going to paste a set of frame details that cover the individual characters and numbers we'll use for the timer. Notice how all of these have a width and height of 8, which is the size in pixels of the standard font in Bomberman. We'll also add a variable that references the font image that we made available in a previous video. Next, we'll create and export a new function called drawText. This function will take a string of text which we'll draw at a designated X and Y position. To do this, we'll use both the frames object and the image data from above and iterate over each individual character in the string, drawing them out to the screen. As this function is drawn into the canvas, we'll also need a reference to its context too. Inside this function, we'll start by creating a local X variable and set it to 0. This will be used in relation to the base X position and used as an offset as we draw each character to the screen. Then we'll iterate over the text using a for-of loop so that we get access to each character. We'll now use the drawFrame function from the template and draw the correct frame at the necessary X and Y positions. As a small optimization, we'll also check to see if the character is a space, and if so, we'll skip this character and function call. Lastly, we'll then increase the local X variable by 8, which we know is the size of the font, in preparation for the next character. Notice we're using this variable with the base X argument to correctly adjust the X position as we draw each character to the screen. With that complete, back in the Battle HUD class, we'll now call this new function within the draw function. For its text argument, we'll create a formatted string literal using both the clock's minutes and second values. We're using the string's pad start function on the minute value here to ensure it's always 2 characters in length, so if this goes below a value of 10, this function will add a 0 character at the front. We'll position the result in the black box on the left of the HUD, which is 32 pixels on the X-axis and 8 pixels on the Y-axis. And while we're here, we'll also draw the player's scores at the correct boxes in the HUD too. We'll use a for in loop this time and iterate over the game state's wins array. This will give us the player's ID or index so we can refer back to their score in the array. Inside this loop, we'll again use the new drawText function, passing on the context and the player's win value, but this time use the base X position of 104 and multiply the current ID value by 32, as this is the gap in pixels between each score in the HUD. The Y position is exactly the same though. Okay, before we check the results in the browser, let's not forget to call the Battle HUD's update function within the Battle Scene's update function, so that the HUD's clock will count down. Checking the HUD's display in the browser now, you can now see we have the game timer ticking down from 3 minutes as expected. We also have all the players' scores showing in their associated boxes too. Good stuff. So that we can determine a winner for the game, we'll now have to adjust the Bomberman's death state so that the players no longer respawn automatically, replicating the original game. Firstly, we'll create a new function called removePlayer in the Battle Scene class, which, yes, as you can guess, this removes the player from the game. This function will follow the same practice as we've done before for other remove style functions, in that we'll find the index of the player using their ID and then splice them from the player's array. Once done, we'll now pass on the function reference to the Bomberman class in the addPlayer function. Then in the Bomberman class, we'll mirror this change and add an onEnd parameter to the constructor, and as per usual add a local reference to it. Next, we'll navigate to the handleDeathState function and update this to call this function when the death animation is complete, meaning they'll be removed from the game. Referring back to the death animation frame array in the Bomberman constant file for a moment, you'll notice we have a -1 for the frame delay in the last frame of this sequence. We've done this so we can easily identify if the animation has been completed. So back in the handleDeathState function, we'll now check if the current frame delay value is a -1, and if so, call the onEnd function passing on the ID property. Doing so means we can also remove the call to the reset function, and to be fair, remove its code entirely as it's no longer required. Back in the browser, as we travel the stage and eventually blow up the other players, you'll notice that they no longer respawn at their starting positions, which is exactly what we wanted and replicates the original game's behaviour. Although, if we go ahead and kill all the other players, we're left stranded with no conclusion. If we were to follow the original game's behaviour again, the game should end, and the remaining players should win the round. So let's look to add this final feature for today in our version of the game. Starting in the Bomberman game class, we'll add a new function called resetGame, which, yes, will look to reset the game. It will take the winning's player ID as the parameter, which we'll use as an index for the game state wins array so that we can increase it by 1. Then we'll reset the scene's property by newing up another instance of the Bomber Scene class, which will fundamentally reset everything in the game, minus the game state. We'll then pass a reference to this function as another argument to the class's instantiation, as it will need this to end the game, so we'll add this to both instances. Then in the Battle Scene class, let's again mirror this change in its constructor. We'll add a new parameter and call this onEnd, then add a local property so we can assign a reference to it. Finally, we'll add a new function called checkEndGame, and call this within the main update function. This will check to see if the game is in an endgame state, and if so, call our new onEnd function. Here, let's initially check to see if the player's array length is higher than 1, which we know means there's more than one player in the game. We'll simply exit this function if so, as we know the battle is still ongoing. If we are down to the last player, we'll now need to ensure that they are still alive, as this could potentially have ended in a draw game, for example when the last two players blow each other up at the same time. So for this, let's ensure the player's array does at least contain one player, and then ensure this player's current state property is anything other than the death state. Finally, we'll then call the onEnd function to complete the round, and use a ternary with the isLastPlayerAlive variable to decide who the winner is. If this is true, we'll pass on the ID property, otherwise we'll pass on a -1, which ultimately means there was no winner for that round. Checking the results in the browser now, once we've gone around the stage and taken each of the other Bombermen out, when we get down to the last player, you'll notice the game will now reset and increase the score of the player that has won. And just to confirm and validate this, we'll use a different coloured Bomberman and do the same on the next round. Again, the correct score is increased when the last player is blown up. And with that, I think we've pretty much done, as we have a complete end-to-end multiplayer game. Nice. I suppose the natural progression from here will be to add the game over and summary screens or scenes when the round ends or when the battle has been won, but that'll be a topic for another video. So before we close up for today, I think we have some time for a little bit of refactoring. So let's take another quick look at the code and see what we can improve. We'll start small, so back in the Bomberman game's class constructor, we'll replace the scene declaration with a call to the resetGame function to remove the duplication. A simple fix, that one. For the next refactor, let's jump into the bomb explosion entity class and simplify the getBaseFrame function. Let's remove the current code, which is a little too verbose at the moment, and instead perform several clearly conditional checks. First, we'll check if the flame cell's isLast property is false, and if so, we know it's one of the middle frames, and therefore we can draw either the vertical or horizontal frame based on the cell's isVertical property. And if it's not, we know the frame is one of the last frames in the explosion, so we'll again check if it's vertical, and if so, use the correct frame depending on whether the location is above or below the bomb cell position. Lastly, if neither of these is true, we know it now has to be a horizontal flame, so we'll do another comparison and return the correct horizontal flame frame based on it and the bomb's location. Next, in the Bomberman class, we'll make another quick change to the player's initial speed multiplier variable. At the moment it's a little low, so we'll increase the value to 1.4 to more resemble the starting speed in the original game. The final two refactors we're going to do today will be more minor quality of life improvements. For the first, we'll apply a Z order on the players, so that when drawing them to the screen, they draw in the correct order based on their Y position. So in the battle scene class, inside the update function, we'll use the sort function on the player's array. If you're familiar with this function, you'll know it takes two entries from the array and applies a comparison function to them. As this function requires a positive or a negative value to sort these entries, we can easily use the player's Y position for this. If we deduct the first entry from the second, and the result is a negative value, we know the first entry should be drawn first, and vice versa, if it's a positive number, we know the second entry should be drawn first. And for the last addition, we'll add a debugging box for the Bomberman's collisions we added earlier. So back in the Bomberman class, in the draw function, we'll add another call to the debug's draw box function. This time, however, we'll use the getCollisionRect function we created earlier and pass those values onto the dimensions array. And for the last argument, I've decided to use a red colour for this box this time. Okay, with that final change, let's see if everything still works. And it seems so. The game does indeed start as normal, the bombs are still drawn correctly after the adjustments, and the Bombermen move around a little quicker as expected. The players are also drawn in the correct order, so when passing through another player, you can see they either appear behind or in front, depending on the Y position. We now also see the collision box drawn over the player, correctly visualising where the collision box is for debugging purposes. But just for completeness, let's turn the debugging off within the game class. Perfect, everything still works as intended. As you can see, we've pretty much completed everything we've set out to accomplish. So what's next? Well, let's go out of our comfort zone and look to make our game work online, so we're able to battle it out with other players around the world. This will require a server though, so something to think about. But that's where we'll wrap it up for today. Thanks to everyone who's following the series and getting this far in the video. I'm curious to what you people think, so please go ahead and drop a comment. If you've enjoyed this tutorial, why not spread the love and hit the like or subscribe buttons, or join my Patreon community where you'll get bonus content not seen on this channel. Either way, thanks for watching, and I'll hopefully see you in the next one. And out.